Hey there, we're going to work a couple problems from your Angular Momentum 1 assignment, and we'll start with number 5. Number 5 says that we have a frictionless platform, mass is 40 kilograms, radius is 2 meters, and it gives us our rotational inertia equation. And it says that it initially rotates at 10 radians per second counterclockwise, so that's going to be positive. In part A, we are trying to calculate the angular momentum of the platform. So our equation for angular momentum, L is equal to that rotational inertia times the angular velocity. So first step, let's solve for that rotational inertia. And we'll use that equation that they gave us, 1/2 mr squared. We'll plug in our numbers. So 1/2, the mass is 40 kilograms. Radius is 2 meters. And then that's squared. So you end up with 80 kilograms times meters squared. Now we can plug it into our equation to solve for the angular momentum. So your angular momentum will equal 80 kilograms times meters squared. And that initial angular velocity was 10 radians per second. So your angular momentum is equal to 800 kilograms times meters squared per second. And then for part B, we're asked a force is applied to the platform at the bottom side to the right, and it's at 1 meters from the axis of rotation, and it's applied for 4 seconds. And we're asked to calculate the change in the angular momentum of the platform. And remember, the equation for change in angular momentum is equal to your net torque times time. And looking at this force here, it would cause this thing to rotate counterclockwise, so it's a positive torque. So first step, let's solve for that net torque. It's equal to your moment arm times the perpendicular force. Moment arm is 1 meter. And then your force is 30 newtons. So the net torque is just 30 newton times meters. Now we can solve for the change in our angular momentum. So change in angular momentum is equal to the net torque, which we found to be 30 newtons times meters, multiplied by the time, which was 4 seconds, and you end up with 120 newtons times meters times seconds. And then the last part, we're asked to solve for the angular velocity of the platform after we applied this torque. And remember, your change in angular momentum can also be found by taking the final minus the initial momentum. And so if we rearrange this for the final angular momentum, it's going to equal your change in angular momentum plus the initial momentum. We solved for the initial momentum in part A, and we solved for the change in angular momentum in part B. So we can just plug in those numbers. So the final angular momentum is going to equal 800 kilograms times meters squared per second, plus our change in angular momentum, which is 120 kilograms times meters squared per second. So the final angular momentum of the platform is just equal to 920 kilograms times meters squared per second. Once we know the final angular momentum, now we can solve for the final angular velocity. So the equation, the final angular momentum, is going to equal the rotational inertia times the final angular velocity. And we could rearrange that equation. So the final angular velocity will equal the final angular momentum divided by the rotational inertia. So we'll plug in our values. We got 920 kilograms times meters squared per second, all over our rotational inertia, which we found in part A, and it was equal to 80 kilograms times meters squared. So the final angular velocity is just equal to 11.5 radians per second. Now let's jump to number 7 on your assignment. Number 7 says we have a thin rod. It's 0.8 meters long, mass is 30 kilograms, and the axis of rotation is there on the left. And it says the rod is at rest, so that's important, we'll underline that. And it's struck by a 0.5 kilogram sphere that has an initial velocity of 8 meters per second, and then it rebounds with a velocity of 2 meters per second. And for part A, it's asking us, is the linear momentum, so we'll underline that, linear momentum, conserved in this situation? So the answer here is no, it's not. And you might be kind of confused because in the past we talked about in collisions how your linear momentum was conserved, but in this situation we do have an external force being exerted at the pivot. So no, because there's an external force exerted by the pivot. And part B says, is the angular momentum conserved in this situation? And the correct answer is yes. And looking at this situation, we said that that pivot caused an external force, but the pivot here, the moment arm is equal to 0, which would mean that the torque exerted by the pivot is equal to 0. So it is conserved, the angular momentum, because the pivot is at the axis of rotation, so your moment arm is equal to 0, which means that your torque is equal to 0. So there's no external torque exerted by our pivot. And then for the last part, it says to calculate the angular velocity of the rod after the collision with the sphere. So our momentum before is going to equal the angular momentum of the rod plus the angular momentum of the sphere. Remember, if an object that's moving in a linear direction has a linear velocity causes an object to rotate like this sphere will, then it does have that angular momentum. So we underline the word at rest. That means that the angular momentum of the rod is just 0 because it's not moving, plus the angular momentum of our sphere. And remember, whenever we have an object that's moving linearly that has angular momentum, it's equal to mvr. So we can plug in our numbers here. The mass of the sphere is 0.5, and its velocity is 8 meters per second. And then that moment arm there is equal to 0.8 meters. So our momentum of the system before is going to equal 3.2 kilograms times meters squared per second. So that's the angular momentum of the system before the collision. And momentum is going to be conserved, so that means that the momentum of the system before has to equal the momentum of the system after the collision. So after the collision, the final momentum, okay, we'll just put an F here, the system, is going to equal the momentum, this new angular momentum of the rod plus this new angular momentum of the sphere. And we want to solve for the angular momentum of the rod after the collision. So I'm going to subtract the angular momentum of the sphere. So the angular momentum of your rod is going to equal that total momentum that we solved for in part 1 minus the angular momentum of the sphere. And so let's go ahead and plug in our numbers. So this angular momentum of the rod after the collision is equal to 3.2 kilograms times meters squared per second. Okay, that's this value, which we found here in part 1, minus the angular momentum of the sphere after it rebound. So we're going to use that same MVR equation, but now we're going to have that new velocity. So the mass is still 0.5. That new velocity is now -2 because we called positive 8 for this first part. So now it's rebounding, so it's in the opposite direction. And then that moment arm is still 0.8. So the final angular momentum of our rod is now going to be 4 kilograms times meters squared per second. And we're trying to calculate the angular velocity. Remember our equation, L is equal to rotational inertia times that angular velocity. So rearrange that for the angular velocity. It's going to equal that angular momentum of the rod divided by its moment of inertia or rotational inertia. So before we can do this, we need to calculate the rotational inertia of that rod. And it's a rod with the axis rotation on the end. So if you look at your list of equations that we have, it would be 1/3 ml squared. So we can plug in our numbers. 1/3 mass, which is 3 times the length, which is 0.8, and then that's going to be squared. So the rotational inertia of the rod is going to be 0.64 kilograms times meters squared. So now we know the final angular momentum of the rod, and we know the rotational inertia. We can plug those numbers in. So we have 4 kilograms times meters squared per second all over 0.64 kilograms times meters squared. And we end up with a final angular velocity of 6.25 radians per second. So hopefully this helps a little bit in working through some of these angular momentum problems, and we're going to do some more practice in class as well.